Okay, let's dive right into this. Welcome to today's Explainer, where we're basically tearing away the curtain on artificial intelligence. A lot of people talk about AI like it's some kind of incomprehensible magic, right? Like it's this mysterious black box that just somehow knows the answers. But honestly, that couldn't be further from the truth. In reality, AI is a highly specialized toolbox. It's a collection of super practical, incredibly powerful algorithms designed to tackle specific problems. So we're going to unpack that very toolbox today and demystify 25 of the most vital algorithms used in machine learning right now. Here is a quick look at our roadmap for this explainer. 1. The machine learning toolbox. 2. Supervised versus unsupervised learning. 3. Clustering data. 4. Reinforcement learning basics. 5. Deep learning neural networks. And finally, 6. Choosing the right AI tool. All right, Section 1, the Machine Learning Toolbox, a quick guide to the most powerful algorithms. And this brilliantly illustrates the whole shebang at a glance. Notice how beautifully this incredibly complex field can actually be organized. We've got 5 distinct, color-coded learning styles running down the left side there, and a total of 25 specific tools spread across the board. Every single icon you see represents a real mathematical engine driving today's technology. Moving on to Section 2, supervised versus unsupervised learning. This is really the foundation of machine learning. So what does this all mean? Well, the core difference literally comes down to the data you feed the algorithm. With supervised learning, you're essentially playing the role of a teacher. You're feeding the algorithm labeled data, meaning you already know the answers, and you're training it to predict specific outcomes for new data. Unsupervised learning, on the other hand, is more like an explorer. You give it raw, completely unlabeled data, and you basically ask the algorithm to go find the hidden patterns and structures entirely on its own. So think of it as predicting versus pattern finding. Let's pull open that first blue drawer, supervised learning. Here are 5 classic tools you use when you actually have that labeled data. If you need to predict a continuous value, like say the price of a house, you grab linear regression. If you need a binary outcome, like predicting if an email is spam or not spam, you use logistic regression. Then we have decision trees, which use these really simple branching rules, and random forests, which brilliantly combine multiple trees to boost your overall accuracy. Finally, support vector machines draw an optimal boundary, or a hyperplane, to perfectly categorize your data points. But remember, they all rely on you pointing them in the right direction first. Now, what's really interesting about the slide is how our source categorizes this next set of algorithms strictly under the umbrella of finding patterns, unsupervised learning. While you might actually see tools like K-nearest neighbors or boosting used in supervised contexts a lot, here we're focusing on their raw structural power. We're talking K-nearest neighbors classifying by proximity, naive Bayes leveraging probability, and heavy hitters like gradient boosting, Eta boost, and XGBoost, sequentially combining weaker models to uncover those deeply hidden data structures. Section 3. Clustering, grouping the data. Or organizing the unknown. You know when you look at a massive spreadsheet of user behavior and you see absolutely nothing but noise? Well, clustering is the exact tool set you reach for. By definition, clustering algorithms mathematically group similar data points together. They find the natural boundaries in your data without you having to tell them what those boundaries should even be. Our source highlights 5 absolutely vital tools here. K-means is your go-to for grouping data into a specific number of clusters, which we call K. Hierarchical clustering takes a totally different approach by building this tree-like hierarchy of groups. dbScan is super fascinating because it groups things based on sheer density, allowing for really irregular, arbitrary shapes. And then we have tools like Principal Component Analysis and TSNE. These are basically your translators. They take incredibly complex, high-dimensional data and reduce it down so you can actually visualize it in a normal 2D or 3D space. They literally make the invisible visible. Okay, Section 4, Reinforcement Learning Basics. Interactive learning. So if supervised learning is a teacher with flashcards, reinforcement learning is more like trial and error out in the real world. By definition, this algorithm learns by interacting directly with an environment. It takes actions, receives feedback in the form of rewards or penalties, and then adjusts its strategy to maximize that total reward. This is exactly how AI learns to play chess at a grandmaster level, or how self-driving cars learn to navigate crazy traffic. The 5 tools highlighted in this purple drawer are just fascinating. Q-learning is foundational. It uses a literal table, a Q table, to learn the value of different actions. SARSA takes it a step further by evaluating the state action reward chain as it actually happens, on policy. As things get more complex, we see deep Q networks bringing deep learning into the mix to estimate values. Policy Gradient optimizes the decision-making policy directly. And then Actor Critic brilliantly combines both. It has one system judging the value of a state and another system deciding on the best possible policy to take. Which brings us to Section 5, Deep Learning Neural Networks, Multi-Layered AI. Now, deep learning is absolutely the engine behind those massive AI breakthroughs we keep seeing in the news today. The defining characteristic here is the architecture. Deep learning uses artificial neural networks stacked with multiple layers. These hidden layers allow the algorithm to process incredibly complex representations of data. We're talking about things like recognizing a specific face in a massive crowd, or translating spoken languages in real time. Looking at the heavy machinery of the modern AI workshop, convolutional networks for images, LSTMs for sequences, and transformers for text, you actually might catch a fascinating little quirk from our source material right here. Take a close look. It actually duplicated the descriptive text straight from the reinforcement learning category. So yeah, obviously a typo in the original graphic, but the underlying reality remains absolutely true. These 5 architectures are the backbone of deep learning today. And finally, Section 6, the right AI tool, our conclusion. Let's move to and see how this builds to our ultimate takeaway for this explainer. At the very bottom of our source material is a statement that really sums up everything we've just talked about. It says, different algorithms solve different business problems. Choose the right tool for the right task. So, the crucial point is this. You wouldn't hire a master carpenter and expect them to use a hammer to cut a piece of wood, right? Well, the exact same logic applies to data science. The success of an AI initiative doesn't come from using the trendiest algorithm. It comes from precisely matching the specific mathematical tool to the specific nature of your data and your business problem. So, we've just unpacked 25 different tools across 5 distinct learning styles. You've seen the predictors, the pattern finders, the groupers, the interactive learners, and the deep network architectures. So, I want to leave you with this question to really think about. Based on the unique data challenges you face every single day, which specific AI tool from this tool belt does your business need to pick up first? Thanks so much for joining me for this explainer, and keep exploring.